I'm going to show you how to solve a couple of systems of equations by graphing. So let's take a look at this system here. We've got two equations, y is equal to half x minus 3, and also y is equal to negative 2x plus 2. Each of these equations represents a line that can be graphed, and we can graph either by plotting points or by using the slope-intercept method. So I think that for the first equation I will use that slope-intercept method. So when we look at the first equation, the coefficient of x is the slope, and that's equal to a half. And so we've got slope is equal to 1 divided by 2, and we can think of that as rise divided by run. So a positive 1 in the numerator means that we are going to go 1 unit up, and a positive 2 in the denominator means that we are going to go 2 units to the right. So that slope tells us where we're going to move in reference to our y-intercept, but our y-intercept is at negative 3, and that's where we're going to anchor on the y-axis. And from that point, then if we go 1 up and 2 to the right, we can plot a number of points, and again 1 up and 2 to the right. And then we can connect the dots to draw the line. For our second equation, we have y is equal to negative 2x plus 2, and again, the coefficient of x is the slope. So our slope is equal to a negative 2. And because we don't have a denominator, we're going to insert one so that we can again determine the rise over run. Rise in the negative direction means that this is actually going to go down, and so we're going to go 2 units down. And in the denominator, we have a positive 1, which means that we go 1 to the right. So that's our slope. And then for the y-intercept, we have a positive 2, and that's where we are going to anchor on the y-axis. So we will have our starting point at 0, positive 2. And from that, we will count 2 units down and 1 to the right. 2 units down and 1 to the right, and as you can see, we intersect the other line at this point. So we can graph the line by drawing it. And with the 2 lines in the graph, we can see that there's a point of intersection right here. If we wanted to mark the coordinates of that point of intersection, we would look in the x direction and see that it appears that the point is about 2 units over to the right, and that the y value is about 2 units down, so that's going to be a negative 2. So we'll write the solution of this system of equations as being the point 2, negative 2. And we could check the solution, but I will leave that for you. Taking a look at the next system, our first equation is 3x plus 3y is equal to 6. And I will graph that equation by plotting points since it's not represented in slope-intercept form with the y isolated. So for the first equation, I'm going to make a table and choose some values of x, 0, positive 1, and negative 1. You could choose any values you like, but these are simple ones. So when I plug in x is equal to 0, I get 3 times 0, and that drops out, plus 3y is equal to 6. And when I solve for y by dividing by 3, I end up with y is equal to 2. For x is equal to 1, I get 3 times 1 plus 3y is equal to 6. And when I subtract 3 from both sides, I get 3y is equal to positive 3. And so y is equal to 1. And finally, for the last point, when I let x equal negative 1, I get 3 times a negative 1 plus 3y is equal to 6. And this time, because 3 times negative 1 comes out negative, I'll add 3 to both sides, and I get then that 3y is equal to a positive 9, and dividing out by 3, I get that y is equal to positive 3. So I can graph each of these ordered pairs. I have the point x is equal to 0 and y is equal to 2. So that's on the y-axis. The second point is the point 1, 1. And the third point is the point negative 1, 3. And I can connect those dots. So there's the graph of the first line. Let's now move on to the second line, where we have y is equal to negative x plus 2. And this time, because the y is isolated, it's in slope-intercept form, so I will use the values of slope and intercept to graph this line. And again, the slope is the coefficient in front of x. We don't see a number there, but we assume it to be 1, and so that number is actually a negative 1, and I can think of it as a negative 1 divided by 1. So when we count, we are going to go 1 down for every 1 that we go to the right. And our y-intercept is at positive 2, and so we will anchor ourselves on the axis at 0, positive 2. And as you can see, we're sitting right on top of the other line. When we use our slope to count down 1 and to the right by 1, we again land on the line, and we can see that all of the points are going to coincide. So when we draw the second line, you can see that there are infinitely many points where both the pink and the blue line coincide, and those are all solutions. And so every point along this line, which is actually a single line, is going to be a solution. We could just say infinitely many solutions, but that would not be descriptive enough because there are many points out in no man's land that lie off of the line which are not solutions. And so when we write the solution of this system of equations, we want to write it in this format. So we're going to put it in set notation and say that the solution, which is again the place where you have points on both lines, is the set of all points x and y, but we want to give some description of that, and so we're going to say such that, that vertical bar means such that, and we'll then choose one of these two equations. It doesn't matter which one, but I think I'll choose the one in slope-intercept form. And I'm going to say that y is equal to negative x plus 2. And what this means is that any point which is an ordered pair, which satisfies this equation, is going to lie on both of these lines, and therefore this is our final solution to the system.